Book 3 now.
Yep.
Okay, cool. So there's no new questions here, but I've slightly updated the document in Keats now, just with a few explanatory details, because I think this was taken from my other course, and it was maybe done at a later point of that course. So anyway, so the video from the skills session today, I think I've just uploaded it, but I've just got to actually put it on Keats. There's a slightly painful procedure that we have to go through to do that, but I can put it up there after this session. So yeah, so obviously homework 3, let ST denote the stock price process for the usual Black-Scholes model, which under the physical measure, i.e. the real world measure, but we've seen that it satisfies this SDE. Well, physical measure it says there, yeah. Mu is a real number, sigma is greater than 0 as usual, and the initial stock price has to be greater than equal to 0. The question then asks, compute the no arbitrage price PST and the delta at time t, so at some point, which is somewhere between 0 and the final maturity time capital T of an option which pays the natural log of ST all squared at the final time capital T, and describe how to dynamically hedge this option. So this is an example of a payoff which you can actually compute the option price more explicitly than you can a European call option, i.e. well, I mean, we do have an explicit formula, but it's still in terms of the phi function, and as we saw, we didn't actually derive the Black-Scholes formula because it's a bit of a mess to do that. But for this particular payoff, which is less common, but it's more convenient for homework and exam questions, we can derive it all kind of quite easily with our bare hands. So from the usual Black-Scholes hedging arguments, although we may have focused mainly in the notes on the European call option case, it's the exact same argument for any payoff, any terminal payoff f of ST. So it's the same argument, which leads to the same argument, that leads to the same PDE we have here. Well, I mean, from the Feynman-Kac formula, we know that it's the discounted. I'm having deja vu. Did I say this earlier? I think I did. I can't remember. I'm getting old. Anyway, it's the discounted value of the expectation under Q of log of ST squared, which is a payoff. Yeah, I did say something like this earlier, didn't I? Given that the current stock price is there. So you should always keep in mind that that's the actual meaning of P of ST. The idea is that we're always at time little t, with the understanding that the current stock price, ST, is equal just simply to the dummy variable S. Okay, so this is the expectation to price this option at any time t. This is the expectation that we need to compute. And under Q, of course, the SDE for the stock price is given by this. So we know, we've seen that, of course, we did it the other way around. In the note, we started off, in the notes, we started off with this, but with R replaced by mu, and then showed that this ST process satisfies this SDE. So we kind of went the other way around, but essentially this formula is consistent with this SDE. And taking natural logs of everything, we see that the this is updated, isn't it? Okay. I mean, I updated this a bit, so I need to make sure that I've correctly done everything. There is no U, so I don't know where you're getting R equals U from. I think to Jian, you'll have to clarify where you're seeing a U variable there, because I can't see one in your input. So the log of the final stock price is equal to the log of the. So in this question, it would be more convenient to express things at the final maturity in terms of things at the intermediate maturity, little t. So I should say, so we're currently here, but then we can rewrite what is here in terms of what is here. which is more convenient for the purpose of this question. So the gunk that we see in the exponential here just relates to what happens from little t to capital T, and the rest of what goes on has been absorbed into this. But if you want to see that, I should maybe put another intermediate line in there. So, if we start from this, then I'm saying, so it would be S0, go away, e to the r minus a half sigma squared t plus sigma wt, and then times another exponential factor, which is the remaining stuff that relates to what happens from little t to capital T. So t minus t plus, still inside the exponential, w capital T minus wt. So it's kind of a decomposition, if you like, but then, sorry, I missed the S0 in it. But this S0 times this start is all just S. Sorry, no, sorry, I didn't miss an S0. This is all one thing, yeah. So this here is ST, so that's that. So we're essentially breaking up ST into the components which come from what happens up to time little t, well, from time 0 to time little t, and then from time little t to capital T. And this is what you end up with. So the conditional, and I'll put that in red because that's a distribution of the terminal natural log, the natural log of the terminal stock, i.e. what we have here, is normally distributed with, so when we take logs of everything here, you'll get the log of S at little t plus r minus a half sigma squared times t minus t, and the conditional variance will just be sigma squared times the remaining time interval, which is capital T minus little t. So, okay, maybe I should put an intermediate line in where I just simply take the natural log of this expression, but I hope you can all do that kind of thing by now. So what we have now, as I said, is that we've obtained the conditional distribution of the log of the final stock price in terms of, and when I say condition, we're conditioning on the information we have at time t. So we know but all we need to know is the stock price at time, at the intermediate time little t, which we're actually thinking of as the current time. So then, using the risk neutral valuation formula, which comes from the Feynman-Kac formula from the lecture notes. And again, if you haven't got to these things in the notes, you might as well just log out now, because this isn't really going to benefit you until you've looked at those things. I don't think I needed to rewrite that, but yeah, it doesn't really matter. So the price of the option is the discounted value of the expectation under Q of the payoff, but the payoff in this particular case is log of ST all squared. But then this is the expectation of something squared, so it's just, something like of the form, what we have here, like E of x squared. But we know that for any random variable x, E of x squared is equal to E of x all squared plus the variance of x. That's just our formula from the first day, which you also should have known before you arrived, hopefully. So this is an intermediate line I've added in just to clarify that point, and I'm then rewriting this expectation of something squared as the variance of that something plus the expectation of that something all squared. So that shouldn't be hang on, but is this okay, I need to check this is the same one I wrote, because I thought I've got a more updated version. Sorry, just take me 30 seconds to check something. Okay, was that? Oh, sorry, that was question 2. Yeah, so I'm just going mad into. Just look ahead to question 2, and sorry, I was getting confused with question 2 here. So getting back to this, so I'm just using this formula here for the specific case of this log ST. So log ST is x in this case, and these variances and expectations also need to be computed under the Q, in the Q world, as it were, under the Q probability measure. So the thing that's stupid there is the Q should just be 2. There is no Q in this question yet. I should say, you should have got a Keats announcement about homework. The skills session. So that graph was wrong. If you remember it was right, but the variable on the x-axis was wrong. So I now redid that graph as 2 separate graphs to make it clearer, and that x-axis is correct now. So you should look at that skills session document as well. after this, but or now if you want. But so anyway, yeah. So getting to the final line, which was there anyway before, then we know that the the second term has gone to the first term here, and this term has gone to here. So yeah, I should have really written this the other way around. But it doesn't really matter. So the variance of log of st we know is just we can just read it off from there. It's sigma squared into capital T minus t. Go away. The expectation, or rather the conditional. Yeah. Okay. Yeah. Okay. I forgot as well. Okay, in this line that I've just added in, these are in fact conditional variances and conditional expectations. So really here it should say given st, and here it should say given st as well. So again, I'll add that in afterwards. But anyway, so what is the conditional expectation? Well, the conditional expectation relevant here is what we see here. Let me just do that more carefully. It's that, but then we have to square that conditional expectation. So that's what we're seeing here: log of st plus r minus r sigma squared into capital T minus little t all squared. So that's our option price at time t, with the understanding that in terms of the stock price at time t, which we often, often we would replace st there just with the dummy variable s, in which case we would have to replace that with s as well. So that's fine. That's the first part done. Then we need to look at the delta of the contract, which is just requires us to partially differentiate this answer with respect to s. To some extent, I haven't written it here yet, but maybe if I was writing that again, maybe you should perhaps, it's better style maybe just to simply write this as P of ST, as I just said, and replace that ST with S. And then we just need to compute the partial derivative of that expression. But I've kind of done that here, but then replaced the answer again, or rather replaced S with ST. It's correct what I've written, but some of you might find it confusing if you're still struggling with the difference between dummy variables and actual random processes. But anyway, but essentially we just need to differentiate this expression with respect to, well, as it's written here, it will be st. So the derivative. So, and note, be careful that you've got this square term here. So because of that square term, it becomes 2 times this term, but without that square anymore, which is just this. But then, because we're using the chain rule, we also have to differentiate the inside there. The only dependence on s or st on the inside is the natural log of st. The derivative of log of st is 1 over st, so that's where that's coming from. So the 2 there is just coming from, because we're essentially, it's like you're just differentiating x squared, which of course is 2x. But then there's also a contribution from the use of the chain rule, which is the derivative of what's inside this bracket with respect to st, which gives rise to this additional 1 over st term. So if you want to hedge this contract, so the understanding there would be is that you've bought the contract, but you're then trying to completely nullify your exposure, i.e. get rid of, eradicate, remove any exposure that you have to this contract, given that you bought it, but with the use of dynamic trading rather than buying another actual option contract. You have to you have to replicate the opposite of this contract. So you replicate minus log of st squared. And to achieve that, you just follow the same general recipe that's in the proof in the note, in the lecture notes. You hold, well, it will be minus PSTT because we have this minus in front now. So you hold minus the delta of the original option units of stock at each time instant, place the remaining wealth or your remaining wealth in the risks bank account. You start off now again with minus P of S00. In the lecture notes, it would be P of S0 because in the lecture notes, we were replicating the original payoff, not minus the original payoff. And then, as usual, your total wealth evolves according to the self-financing rule. As here's your contribution from changes in the stock price, which is a stochastic integral term, but it's the shorthand that we use for that. And here's what you're making from the money in the risks bank account, or it may be this quantity could be negative, in which case it means you're borrowing money. And then the solution, again, from the general argument in the notes, is not obvious just from here, but it comes out from the general proof in the notes that the solution to this self-financing STE, if you like, is given by simply because, again, we have the minus here. It's minus the option price that we're considering. So in particular, XT is minus ST squared. So this whole strategy here gives rise to a payoff of minus log of ST squared. But then the understanding is this, that we've also bought the contract that pays that. So if you bought something that pays log of ST squared and then come up with a replication strategy which pays the opposite of that, i.e. minus it, then net your total sort of exposure at expiry is zero. So you've successfully hedged the contract, you've hedged your risks. Think of it just as insurance, if you like. You're ensuring that if your house burns down, that you will receive exactly the price of that house, that kind of thing, but minus the sentimental value of it. Anyway, so question 2. So it is only 2 questions, but they're reasonably substantial questions. Says compute the no arbitrage price at time 0 and at a general time t of a contract that pays ST squared at time t, and then at the end it says set R equal to 0, and suppose that, we'll get to that because it's going to be too to talk through that at the moment. So we'll do the more standard part. Okay, so from Ito's lemma, we know that the natural log of the stock price process, which we usually refer to as XT, satisfies this SDE. We've done this a few times already, I think, in the videos anyway. So when we integrate this expression from little t to capital T, we get the following: x capital T is equal to xt plus r minus a half sigma squared capital T minus little t, and sigma times the change in the Brownian motion. And this is just a constant, and this is just a constant, so they don't really have any non-trivial effect when we perform that integration. They are just constants that come outside the integral. So from that, we see that okay. So I changed how I wrote this question to make it more consistent with the idea of conditioning and what happens at time t. So, okay, this is true simply because ST is go away. ST is e to the xt, and therefore ST to the p is e to the p of xt. So that's trivial, but actually what I also want to be able to say is that this is true given ST and given XT, because having the information about ST, having the knowledge of ST is the same as having the knowledge of XT, because of course if you've got one, you can just get to the other by either taking the log or exponentiating. So this is true, but it's also true if you the conditioning version of that is also true. So then we can say that XT, the log stock price at the final maturity, is conditionally normal with mean mu1 sigma 1 squared, where mu1 is so again I should really say XT conditioned on, say, XT, which is the same as conditioning on S at time little t, has this conditional mean, so it's the current value of x at time t plus this drifter. Otherwise, it's just exactly what we see here, and the variance is just the variance of this quantity, which is sigma squared times the remaining time. So that then the expectation of q of e to the p of xt given xt is, so here I'm using, we know that xt is just, conditioned on the information at time t, it's a normal random variable, so we can use the general formula for the moment generating function of a normal random variable, which is discussed in the first live session. So it's then just a question of, what is the mu1 and the sigma 1 for this particular question? Well, we've already written them out. Here was mu1 and here was sigma 1, so then we just have to plug these in. So there is an xt there that gets multiplied by p, but when you then rewrite xt in terms of log of st, this comes out as a factor, which is just st to the p, and then the remaining contributions from the terms are just p times mu1, the remaining part of mu1, which is that, and then a half sigma 1 squared, which is this, times p squared. And this is a very useful formula, which I think we use many times. I think earlier today, this document just said something like, as we've seen many times, but that's because I'd taken this question from my other course where we had done it many times. So I've had to actually go through this from scratch now. So, yeah, so it's important to look at this, and I will add in these clarifying things about the fact that we want to be conditioning here and here as well. So anyway, in the question, our specific interest is in the case when, actually, is it? Yeah, we're looking at ST squared. So P, the relevant P value that we're interested in now is when P is 2. So the option price is the discounted expectation under Q of the payoff. Well, at time, we're conditioning at time little t, so condition on, it's just this formula with P equal 2. So that's what we're plugging in there. P is 2 leads to this. So, so a half times P squared when is a half times 2 squared, which is 2. So that's why we get a 2 there, net. And then you can tidy that up a little bit, I think, because you get 2 sigma squared into capital T mod little t there, but minus a half sigma squared times 2, lots of that. So there's a cancellation of 1 sigma squared T, so you're left with this. Okay. Now, so that's the option price. That's our formula for the option price. The option price being an option which pays this at time t, and this is the unique no arbitrage price of that option at any earlier time little t, up to, which could be anywhere as large as, well, you know, the usual thing that 0 is less than equal to t is less than equal to capital T. So now you're being asked to compute the Greeks. Well, okay, I didn't actually read out the so it says now set the interest rate equal to 0 for simplicity, and suppose that we delta hedge this contract at time 0, but not after time 0. So it's saying let's put a delta hedge in place at time 0, but we don't do any subsequent delta hedging after that time. And then the question is, do we want more or less variability of S over a small time interval 0t? Well, first of all, let's compute these Greeks. So to compute the gamma, you need to differentiate this twice with respect to S. So when you do that, the only S dependency is the S squared. So you differentiate once, you get 2S. Differentiate again, you just simply get 2. And remember, for simplicity, I've said let's just set R equal to 0, so there's no contribution from that or that. So the gamma comes out to be that. The theta, again, we're knocking out the R terms, so that and that, just to make it, otherwise it's just going to be a bit of a mess, and it's not really going to teach us much more. So note that we have a minus there, so you end up with minus, and my convention is that my theta is with respect to little t, not capital T, so that's something to be aware of. So because of the minus there, you end up with a minus sigma squared times the existing S squared times that, and again the R terms have vanished. So but recall also that from the Black-Scholes PD, we know that these two expressions, the theta and the gamma, are related. When the interest rate is 0, the Black-Scholes PD is precisely just a relationship between the theta and the gamma of the option for whatever payoff we're considering. So this is theta and this is gamma. So essentially theta plus something times the gamma is equal to 0. The something being a half sigma squared S squared. So yeah, so as I said, it says the Black-Scholes theta are intimately related. So in particular, for any option payoff, the gamma and theta must, or at least when R is 0, the gamma and the theta must have opposite signs because their sum is equal to 0. So now, for this specific question, you're being asked to consider a small time interval. So we dt, and this sort of double less than symbol just means like consider this quantity very small. It's just kind of an informal notation of that. Then if we perform so remember the understanding is, so we've bought the option which pays ST squared, but we've also delta hedged it at time 0. So our profit and loss is equal to the change in the value of the actual option itself minus the profit and loss which accrues from that initial delta hedge that we put on. So the initial amount of stock, we initially sold PS of S0 and 0 units of stock, because the delta was Well, yeah, I don't care about the actual formula for it, but the delta of the option is PS of that. But if we're delta hedging, then we have to sell minus that amount, which is why we've got a minus there. So if we then perform a Taylor series, well, it's a multivariable Taylor series expansion of the change in the option price itself, you get PS times DS plus a half PS DS squared plus PT DT plus some higher order terms, which I mentioned here, which I'm just going to ignore for practical purposes of this question because their higher order will be relatively insignificant compared to the terms we're actually looking at here when this DT is indeed very small. So I'm just the terms I care about. But what we do see then when we do so, what I'm using here is like the 2D version of Taylor's theorem that says say f of sorry, I don't have much room on this desk, but f of x plus a small change in x. Oh well, let me f of x plus dx and y plus dy, if the function f is sufficiently differentiable, is approximately given by f of x y plus, say, f of x y dx plus f of y. There's not much room for this, isn't it? Fy dy squared plus also some second order terms as well. So if we're going to higher order, dx squared. I mean, actually, I'm not doing all the second order, using all the so this goes on, and there is also a mixed partial derivative and a dy squared. So this is really just, as I said, I'm just using the two-dimensional version of Taylor's theorem. But there are certain terms which I'm ignoring without completely rigorously justifying why I am ignoring. So I'm ignoring terms of order ds dt and ds cubed. I mean, ds cubed terms are clearly smaller than ds squared terms, which I am retaining. But it turns out that the dt squared terms, because of how Ito's lemma work, are also higher order than these ds squared terms that I'm keeping. But the main thing is, anyway, that this delta term cancels out with this. Because we're delta hedging, the first order contribution to the change in dp has been completely cancelled out. That's the whole point of delta hedging. So what you're left with is the sort of higher order contribution due to gamma and theta. Now the question is then asking, if we've done this thing, i.e. we bought this S squared contract, remember, that's what you're asked to consider, but also delta hedge times zero, do we want the stock price to do a lot or not? Well, you can see that yes, we do, because your profit first of all, I should say the gamma of this thing is positive, I guess. Yeah, so as we saw there, the gamma is positive, which means the theta has to be negative. So the larger the change in the stock price over this small time interval, the more money you make. It doesn't matter what the direction of that change is, you just need there to be some action, basically. Conversely, if not much happens, you get killed by this term because this theta is negative and that gets multiplied by dt. So this is really the game. If any of you actually become option traders, this is the game that you play all day. It's a game, but it's this trade-off between delta and not between gamma and theta. You would typically delta hedge so that you can then just focus on trading volatility. And by volatility in this case, we just mean that you're just trading the ds squared term. So in this case, as I said, when you've got a contract which has positive gamma and hence negative theta, you really just want to bet on there being a lot of action, a lot of movement in S, so that ds squared is large, because otherwise this term is like a term that is just draining away against you, kind of thing. And it's often why they call this, it's quite a dramatic phrase, they call this bleed sometimes on theta. They often call it bleed, because it really, in this case, when your theta is negative, it is kind of like you're kind of, unless there's some action, you just kind of bleed out and go bankrupt. So, but conversely, if we rigged up the question the other way around and considered the payoff of minus st squared, then it would be the other way around. The gamma would be negative and the theta would be positive, and then in that case, the bleed would be more of a growth. It would be a good thing for you, and you would then essentially be betting or wanting there to not be much action, i.e., you would want DES squared to be very small. So this kind of clarifies also the sense in which it's a fair game. I mean, remember we've built into our Black-Scholes model that there is no arbitrage, so you can see that there's no free money here. You know, if the profit and loss had this there without this term, you'd be thinking, well, okay, you know, it's just all upside with no kind of downside or no kind of you know, consequences of, you know, that risk taking kind of thing. So this really captures the trade-off of delta hedging options, that it's really like you're either betting on volatility, i.e. DS being large, in a small space of time, or the opposite way around. If your gamma is negative, then you really don't want much to happen over that small time interval. So that's quite a nice analysis. It really gives you a feel for how this kind of thing works in practice. And often in practice, the option, I mean, they wouldn't generally be trading ST squared contracts in practice. They would be trading, for instance, the barrier option, or even just a standard European option. Remember, for a standard European option, whether it's a call or a put, the gamma is actually positive. So you would be in the case where the gamma is positive here and the theta is negative. So that's all for these questions. Then, does anyone have any questions on those questions? Yeah. Hello. I can't see any questions unless everyone's logged off or something. Okay. Well, if there aren't, then yeah, as I said, if you suddenly a question comes to you after you look over this, then shoot me an email or on Teams or whatever. Email is better than Teams, and otherwise, again, I will upload this video now as well and do it quicker than last week. The other one is it's already been uploaded. I just need to actually sort of copy and paste it into Keats, the skill session. I mean, so otherwise, yeah, that's fine. You've had lots of practice on this Black-Scholes stuff now. So enjoy your week off, and I guess I'll see you in 2 weeks. I think, yeah.